We're going to start a series of video lectures on exponential functions. And we're going to begin by comparing exponential functions to linear functions to see what the differences are. So our objective here, given a table of values, determine whether a given function is linear or exponential, and find the function that models the data. So what do we know? Well, we certainly know what a linear function is, so let's review that. A linear function is a function of the form f of x equals mx plus b. And we've seen that for some time now, probably starting around middle school or so, whenever you took Algebra 1. Now, what do we know about this linear function? Well, the letter m stands for the slope, which we've talked about when it comes to functions, is the same as the average rate of change. And we know that this slope is a constant. The average rate of change is a constant. Okay, I'll underline that. The average rate of change is a constant. And we also know that b is the y-intercept, the value of the function when x is equal to 0. So now let's define what an exponential function is. An exponential function is a function of the form f of x equals c times a to the x. Okay, so an exponential function has a variable in the exponent where, okay, a, which is the base, is a positive real number. In other words, it's greater than 0, positive real number, larger than 0, and a is not equal to 1. Because if a is equal to 1, 1 to anything is 1, and we're not going to get anywhere. Okay, so a is a positive real number, and a is not equal to 1. C, well, c cannot be equal to 0. Again, if we put c equals 0, 0 times anything is 0, and we simply have the horizontal line, f of x equals 0, which is the x-axis. So c cannot be equal to 0, and c is a real number. Okay, anything you want, positive, negative, it's a real number. The domain is the set of all real numbers. In interval notation, the domain is negative infinity to infinity. Okay, the base, this letter a, the base a, is called the growth factor. How the exponential function grows. And we'll make use of that in this video lecture as well as upcoming video lectures when we look at some word problems. So the base is the growth factor, a is the growth factor. The letter c is called the initial value of the function. Now, if you recall, we go up here. You know, we can find the 0, we can find the value when x is 0. Well, it's the same idea here. When I put 0 in for x, f of 0, a to the 0 is 1. And so so the answer becomes c. And as we look at growth and decay, and we look at some real life problems, the initial value is going to be c, because we're going to start at time 0. And finally, the ratio of consecutive outputs. Okay, the ratio of consecutive outputs is a constant. So contrast this with the linear function, where the average rate of change is a constant. In an exponential function, the ratio of consecutive outputs, the ratio of consecutive y values is a constant, and we're going to see that in just a minute in an example. Okay, so this is some details about exponential functions that we're going to be looking at in the next 2 or 3 video lectures. So let's take a look at a couple of examples with tables of values and to determine whether or not they are linear or exponential. And I'm going to grab my calculator. Just a second here, I forgot to do that. So that we can put them in the calculator and see the graphs. Okay, is the given function linear or exponential? Determine the function. So what is the function that models the data? Now in example 1, I'm going to call the function f of x, and these are 5 values that apply to the function f of x. And you'll notice I skipped a line. I did that on purpose so I can do the change with some space here. Okay, the average rate of change and the ratio of consecutive outputs. So let's do that. So we have 5 points. The slope is the average rate of change. Well, we know the average rate of change is the change in y over the change in x. Okay, I'm going to go from lower number to higher. I'm going to go from down the list to up the list, if you will. So this is equal to 2 minus 5, the change in the y's, 2 minus 5, divided by the change in the x's, 0 minus negative 1. All right, so let's see, 2 minus 5 is negative 3. 0 plus 1 is 1. This comes out to be negative 3. Okay, let's work our way down and see what we have here. Let's now look at the average rate of change between the next 2 points in our table. Again, the slope is the change in y over the change of x, the average rate of change between these 2 points. Okay, I'll go from this one to this one. So this will be my point 2, my point 1. So negative 1 minus 2, negative 1 minus 2, 1 minus 0. Well, negative 1 minus 2 is negative 3, and 1 minus 0 is 1. And so that division problem is negative 3. Let's do the next set of points. Again, moving right along my sets of points to find the average rate of change. Negative 4 minus negative 1 is the change in the y values. 2 minus 1 is the change in the x values. Well, negative 4 minus negative 1 is negative 4 plus 1, and that's negative 3 over 1 again. Hopefully you're seeing a pattern that our average rate of change is a constant. Okay, let's go to the last 2 points. Change in y over change in x. Negative 7 minus negative 4. Divided by 3 minus 2, change in x. Okay, negative 7 minus negative 4 is negative 7 plus 4, and that's negative 3. And again, 3 minus 2 is 1. So again, we have negative 3. So, what do we know? Our average rate of change equals negative 3, and it's a constant. Our average rate of change between any 2 points is a constant. It's always negative 3. If we go back to here and we look at our notes from our linear functions, it's a linear function when the average rate of change is a constant. So this tells me right here that I have a linear function. Okay, so it's f of x equals mx plus b. That's the definition of a linear function. The slope is the average rate of change. So f of x is the slope. Well, that's going to be negative 3. Average rate of change is our slope. The y-intercept is the value when x is 0. When x is 0, our y-intercept is positive 2. So this is the equation. This is the linear function that models the data from this table. So we have a linear function, and this is the equation that models the data. Let's take a look at our calculator. Okay, we think negative 3x plus 2. Go into here. Let me get into let's clear out what I have in here. Again, it's negative 3x plus 2. Negative 3x plus 2. We can graph that, and you can see it as a linear function. In this case, it goes down from left to right. And if we want to go to our table of values, hopefully my table is okay, they're set up. Let's take a look. When x is negative 1, you can see 5 comes out. When x is 0, you get the value of 2. When x is 1, out comes negative 1 as a y, 2, negative 4, and 3, negative 7. So the table of values matches up to this linear function. Let's contrast this with an exponential function. Okay, so here we have another function. I'm calling it an exponential function because that's what it's going to be, but we're going to pretend we don't know that. This is the g of x function, and this is 5 points on the graph of this function. Negative 132, 0, 16, 1, 8, 2, 4, and 3, 2. Let's look at the average rate of change. Okay, a change in y over a change in x. 16 minus 32 divided by 0 minus negative 1. 16 minus 32 is negative 16 divided by 1. I believe we'll come up with negative 16. There is the average rate of change between these 2 points. Let's take a look between these 2 points. Again, let's look at the average rate of change between these 2 points. 8 minus 16, change in y. 1 minus 0, change in x. 8 minus 16 is negative 8. Of course, 1 minus 0 is 1. So now we can already see that this function is not linear, because a linear function, if we look up here, has a constant average rate of change. This function does not have a constant average rate of change. We've only done the average rate of change between 2 sets of points, and we notice they're different. So this is quickly noted, this is not a linear function. Let's take a look at these next 2 points. Change in y over change in x. 4 minus 8, change in y, over 2 minus 1. Well, the denominator is 1 again. 4 minus 8 is negative 4. And then finally, between the last 2 points, the average rate of change, 2 minus 4 over 3 minus 2. Again, I have a 1 in my denominator. 2 minus 4 is negative 2. So we can clearly see here we do not have a constant rate of change, a constant average rate of change. So now let's take a look at our consecutive outputs, the ratio of our consecutive outputs. Now we can see here, if you look, there's a pattern here. Wait a second, divide by 2, divide by 2, divide by 2. You'll see a pattern. If there's no, but we'll see it here when it comes out, but you should note here, wait a second, something's going on because there's a very similar pattern happening between these numbers. As these go up by 1, there's a pattern going on here. Let's look at the ratio of the consecutive outputs, the consecutive y values. I'm going to look at the y values. Okay, so the ratio of this is going to be 16 over 32. 16 divided by 32. Ratio of y values. That's 1/2. 8 over 16. That's 1/2. 8 divided by 16. 4 divided by 8. Again, these are my y values. I want the ratio of 2 in a row. Okay, consecutive. 4 over 8. Well, that's also 1/2. 2 over 4. That's also 1/2. So the ratio of consecutive outputs is a constant. Okay, so let's note that down here. Ratio of consecutive outputs equals 1/2, which is a constant. They all equal 1/2. So now we go back to our definition for exponential functions, and we note the ratio of consecutive outputs, the ratio of the y value of consecutive y values is a constant. We have an exponential function. All right, exponential function. Okay, that is going to be f of x is equal to, let's go back to what we just learned previously here. A function, it's an exponential function on the form f of x equals c, the initial value, times the base a which is the growth factor raised to the x power. Okay, so c times a to the x, so f of x, what is our initial value? Well, when 0 went in, 16 came out. That's our initial value is when x is 0. So our initial value is 16. And I'll put a dot for times. What is our growth factor? This. This is our growth factor. So 1/2 to the x power. And there's your exponential function right there. So this piece here, let's go back to here. The base is called the growth factor. Now in this case, we're growing, and we're growing by 1/2. So honestly, we're shrinking by, this is kind of shrinking by we're shrinking down, but the growth factor is growing by 1/2 right here. Now let's put that in our calculator. I'll slide this over, get my calculator in here, because I want to look at those. I want to look at this function we have and make sure it lines up with our table of values. So I'll go back to y equals. I'll clear out the linear function that was in there, and I'll do 16. You can write it this way if you want. Just put it in parentheses, 1/2 raised to the x power. Exponential function. Let's graph it. Here it comes, I think. There it is. There's our exponential function. All right, it looks like it's pretty much stuck to quadrant 1 in this case. And let's go to our table of values. So let's go to second table. And let's see. -1, I get positive 32, and that's right here. 0, 16 is the second row. 0, 16, 1, 8, 1, 8, 2, 4, 3, 2, 2, 4, 3, 2. And if I go into my quadrant 1, because it looks like this is all in quadrant 1, you can see this is my exponential function. And in this case, it's not growing, it's decaying, so it's negatively growing, if you will. We started up with a lot, and we're coming down, 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 down. So that's a look at an exponential function, which we'll look more at in our next video lecture. So again, let's go back and review a little bit about exponential functions. A, the growth factor is a positive real number, but it cannot be 1. C, which is our initial value, what happens when you put 0 in for x right here into the function. That's in front here. And most importantly, when you see an exponential function, the average rate of change is not a constant, though there is a pattern. What's a constant is the ratio of consecutive outputs, the ratio of y values.